Welcome all. So today I'll be talking about biological neural models and more precisely Leaky integrated fire model, which is one of the popular methods to design spiking neural networks. And as we're talking about SNNs, so these are mostly defined by differential equation, right? But before that, let's again recall about our most famous artificial neural network models. So these are the models comprised of a bunch of nodes connected with each other with some weights. And after that, we assign some kind of rules to each of these units and then propagating to other units based on weights. For example, we have some rules for forward pass or the backward pass, right? And based on that, we're kind of updating the weights, and based on that, any kind of activities where we are able to perform. Now, let me explain how it is different in case of a spiking neural network model. So in general, spiking neural networks are time domain architectures. Hence, we need to define them with some kind of differential equations. As these neurons are time dynamic, which means we need to see how they behave with respect to time. And then we need to simulate and update the states by going back to the time. Now, don't worry, I'm not going to explain how to solve differential equation because these are numerical simulation that might get a little difficult to understand. Rather, I will explain about event-based simulation. Now, generally, spiking neurons imitate biological neurons. So they have some sort of spikes, I would say, or action potential. Now, we can note as it a voltage. Now, we'll be looking at the derivative of voltage with respect to the time. Now, when the voltage crosses a threshold, some spike or action potential occurs. Now, if you see this example, in plus 40 voltage, there is a spike and suddenly it goes down nearly minus 70 Hertz and then it kind of exponentially decays. Now, after that, what happens? The membrane potential reset or go to some refractory period. Now, here we can see when there is a spike in plus 40 voltage and it's going down till minus 70, minus 70 could be a refractory period. Now, in that period, if we won't provide a higher threshold, then we might not see any spikes. Now, based on these spikes, the neurons communicate, right? But exactly these spikes are very fragile, I would say, not fragile, these are very short, as in it's just a rapid up and fall of the signals. So these spikes are very, very quick, right? Now, instead of designing this short-term voltage fluctuations, we can design based on some particular events, whatever happens at some specific time. And based on that event, we can design our model. Now, mathematical and biological details could be helpful to model such kind of complex computation. But here we only care about the event, which is once you cross a threshold, we consider it as a spike and then we reset. Now, for a faster simulation, we can consider a simple model which kind of follows some functionalities of a biological neuron and also easy and efficient to code, right? Now, let me explain. This is one of the example I have created, a Leaky integrated fire model using Nengo graphical user interface. I would say this is one of the easiest way to design. So here it comes the Leaky integrated fire model. This model explains that the spike decays exponentially. Now, if the spikes cross some threshold, the neuron will emit some spike of its own, and then it will reset. Now, all this spike and reset will happen exponentially. Now, if you see this code, there is a stimulus. The stimulus will provide some kind of input to our neuron. And in this model, particularly, this is the inbuilt example by Nengo, and thanks to them, they have designed such user-friendly model, I would say. I mean, it's easy to code. So here I have given only two neurons, and those two neurons will behave like a Leaky integrated fire model. That means it will on and off based on our input. Now, when our stimulus or our input will be higher, let's say here 0.85 is the stimulus. So that means only one neuron will activate max, the other will fluctuate. Now, this is one of the simple implementation again. The tuning characteristic of this neuron have been defined by one will be on and one will be off. And when the input is high, one neuron will activate and the other will not activate it at that point. Now the characteristics will be reversed based on our input. And here we are providing input through our stimulus. Now, when the input is 0.85, you can see the firing pattern, we can see only one part is activating now in a faster way compared to the other. It's just like a switch. Now this is the second part where the stimulus is minus 0.85, which is completely negative of what we have given in our previous model. And you see only the left-hand side of the neuron is activated and the other is fluctuating. So this is one simple example I have created using Nengo graphical user interface. And let me explain the code a little bit. So you can provide a neuron, and we are kind of ensembling the neurons using the dimension factor and the number of neurons we are trying to do. And then we're providing the distribution for individual neurons that you can customize however you want to do. And the max firing rate, we are kind of providing how much energy it's gonna use. Like here I have given 100 each. And then the encoder will connect with the neurons. And for that, we need to provide some kind of stimulus. And then we need to connect the stimulus with the neuron, and we need to provide some kind of weight, right? So here we're providing the synapse that is 0.001. And based on that, the neurons will be connected with each other for firing their activity. I hope this is easy to understand.